Good morning, children. So today we are going to start a new chapter, sets. So let us start with the definition of set. So it says a set is a well-defined collection of distinct objects. So set is nothing but collection of well-defined distinct objects. And here by well-defined we mean that there should be no confusion regarding inclusion or exclusion of objects. Okay. Here objects in a set are called its members or elements. Okay. Next, we denote sets by capital letters such as A, B, C, X, Y, Z, etc. And members, or you can say elements of the set, are denoted by small letters. Next, suppose if A, okay, suppose there is an element A, okay, which is in set A, okay. So we write it in this manner, okay, A, and this symbol is of belongs to, okay. So we read it as A belongs to A, which means A belongs to A, or that A is an element of A, okay. So suppose this element A is in set A, then in short we write like this, okay, A belongs to A. This symbol means belongs to. Next, suppose that this element A does not belong to the set A, okay, then we write it in this manner. A does not belongs to A, okay. Now let us try to understand sets by few examples, okay. So here, number one, the collection of all vowels in English alphabet is the set containing 5 elements, namely A, E, I, O, U, okay. So here when we say a set of vowels in English alphabet, then in that set we'll have only these 5 elements, okay. A, E, I, O, U, okay. So it's a well-defined set. Next, collection of all even natural numbers less than 10. So if we are collecting all even natural numbers less than 10, so in that set we will have 2, 4, 6, 8 only, okay. So this is also a well defined, okay, because in this set you cannot put 10 inside this, okay. You cannot consider 10 to be the member of this set, okay, because here clearly it says collection of all even natural numbers less than 10. So in that set you will have the elements 2, 4, 6, 8. Next, the collection of all prime numbers less than 20. So we are talking about collection of all prime numbers less than 20. So in that set we will have only these elements 2, 3, 5, 7, 11, 13, 17, 19, okay. We cannot have 23 over here, okay, in this set, because though 23 is a prime number, but it is not satisfying the condition less than 20, okay. So we are considering only those prime numbers in a set which are less than 20, okay. Next, we denote the set of all natural numbers, all integers, all rational numbers, and all real numbers by this. So in class 10 only, I think most of you have come across these symbols. So this N is for natural, this Z is for integer, this Q is for rational, and R is for real numbers, okay. Next, the collection of all beautiful girls of Sikkim is not a set, okay. So we know that definition of a set says that set is a collection of well-defined distinct objects, okay. So here we are making a collection of all beautiful girls of Sikkim. So this cannot be a set, okay, because the term beautiful is not a well-defined, okay. For some people the set will be different. For some people in set they might include someone, okay. So it is not a well-defined, okay. Similarly, rich person, honest person, you cannot have collection of rich persons as a set, okay. You cannot have a set of honest persons, you cannot have set of good players, you cannot have set of old people, you cannot have set of young men, etc., okay, because here these terms are not well defined, okay. It varies person to person, so we cannot get a unique set for it, okay. Like in this case, if you ask anyone, okay, that make a set which will contain only prime numbers which are less than 20, so you will find that everyone will give you the same set. Yes, but here if you ask four people and tell them that make a set of beautiful girls of Sikkim, then you'll find that everyone will have different sets. Okay, in this set they'll have a name of different people. Okay, different girls. So it is not a well defined. Okay, so set is nothing but collection of well defined distinct objects, and by well defined we mean that there should be no confusion, okay, about the inclusion and exclusion of any object. Clear? Now next is how do how to describe or specify a set. So how do we write a set? Okay, so there are two methods of describing a set. So one is roster form, or we call it tabular form. Next is set builder form. In roster form, what do we do is, in a set we write the uh, elements separately. Okay, and each element is separated by a comma. And in set builder we simply give a rule, okay, by which all the elements are defined for that set. So let us try to understand by these examples. So here, write each of the following sets in roster form. So here I have got a set A. So set A is of all factors of 24. Okay, so we have to write this in roster form. So first of all we have to find all the factors of 24. So factors of 24 are 1, 2, 3, 4, 5, 3, 4, 6, 8, 12, 24. So now what we'll do is we will write these elements, okay, separated by comma in this set. Okay, so this was the set that we had got. Okay, A, set of all factors of 24, and in roster form this set is written in this manner. Okay, so here you can see that is you are writing each and every element separated by comma for this set. So this is called roster form. Next is set B, which is set of all letters in the word mathematics. Okay, so what we'll do is, here we can see that the word mathematics consists of these letters MATHEMATICS. Okay, but here when we are writing in the set form, roster form, we will not repeat any letter. Okay, so here you can see though M is appearing two times over here, but in set we'll write only once. Okay, so M comma A comma T comma H comma E comma I comma C comma S. So B equal to this. So this is in the roster form. So here it may be noted here that the repeated letters are taken only once each. Okay, now let us see set builder form. Here it says write the set A. Okay, so this is the set A, and we have to write this in set builder form. So in set builder form what we will do is we will try to observe the pattern of these elements. Okay, here you can see that each elements over here are natural numbers. Okay, and they are less than 8. Okay, so instead of writing them separately one by one, okay, what we can write is, we can write in this manner: A equal to X such that, okay, where X is a member of natural number and X is less than 8. Okay, so the same set is this. Okay, the only thing is here you can see that each elements are written separately. Okay, but in this case you are defining it through a rule. Okay, so here the first part is X, which denotes you have got elements X, and X will be a natural number and X has to be less than 8. So obviously here you can take in place of X 1, 2, 3, 4, 5, 6, 7, but you cannot take 8. Okay, though 8 is a natural number, but here the second condition is not satisfied. 8 is not less than 8. Okay, so this is called set builder form for this set. Okay, write the set B, which is given as this 1, 2, 4, 7, 14, 28 in the set builder form. So if you try to observe the elements over here, okay, here you can see that each element over here, each number is a factor of 28. Yes, because 1 divides 28, 2 divides, 4 divides, 7 divides, 14 divides, and 28 itself divides 28. Okay, so you can see that here this is a set of factors of 28. Okay, so this set can be written as this way: b equal to, in bracket, x such that x will be a natural number over here. Okay, and x is a factor of 28. Okay, next write the set C. Okay, and here C is given as this: 2, 4, 8, 16, 32. Okay, so here if you try to observe, this is 2 to the power 1, this is 2 to the power 2, this is 2 to the power 3, this is 2 to the power 4, this is 2 to the power 5. Okay, so this set C in set builder form, we can write it in this manner: x such that x equal to 2 to the power n, where n belongs to natural number and n has to be less than equal to 5. Okay, write the set D. Here D is given as this: -6, -4, -2, 0, 2, 4, 6. Okay, so here if you could observe, it is -3 into 2, this is -2 into 2, this is -1 into 2, this is 0 into 2, this is 1 into 2, this is 2 into 2, this is 3 into 2. Okay, so this set contains all multiples of 2. Okay, but they are multiples of 2 and they are integers, and they are greater than -7 and less than 7. Okay, so here we can write this in this manner: 2x, okay, such that x has to lie between -3 and 3. Okay, and x is integer. So obviously when you, in place of x, if you put -3, then you will get -6, then you put -2, you'll get -4, then put -1, you'll get -2, you put 0, then you'll get 0, if you put 1, then you'll get 2, so on. So you'll get all the elements of this by this rule. Yes, so this is the set builder form of this given set D. Next is empty set. A set containing no element at all is called the empty set, or the null set, or the void set, denoted by, this is called phi. Okay, its O is there and what vertical line is there. So this is called phi, or simply curly brackets, okay, parenthesis, and here without any element inside this. Okay, a set which has at least one element is called a non-empty set. Okay, so empty set means it has no elements, and non-empty set means at least it has one element. Examples of empty set. So here I've taken one set which contains elements x, and here x is lying between 2 and 3, and x must be natural number. But here we can see that in between 2 and 3 there are no natural number, so clearly this is an empty set. Next set is x such that x is a number and x is not equal to x. Okay, we cannot have a number which is not equal to itself only. Okay, like 2 is equal to 2, 3 is equal to 3, 4 is equal to 4. So, but here is saying we are taking a number x, but that number is not equal to itself. So we cannot have any number which is not equal to itself. So it is an empty set. Next is x such that x is a real number and a square of x should be equal to -1. Okay, so square of x is -1, that means x equal to plus minus square root of -1. And you know that for real number this plus minus square root of -1 is not defined. Okay, if in place of r over here, if we had c, complex numbers, then we could have said that in I square is -1. But here x has to be a real number, so we don't have any real number whose square is -1. So this set is empty set. Next, x such that x is an even prime number and x is greater than 2. This is again an empty set because we know that there is only one even prime number and that is 2. Okay, but here we are talking about even prime numbers which is greater than 2. So we don't have any even prime number greater than 2. So this set is empty set. Next is a set x such that, okay, set which contains x such that x square is equal to 9 and x is an even integer. Okay, so here we know that x square is 9. That means either x is 3 or minus 3. Okay, but 3 and minus 3, they are not even. Yes, but here is saying x such that x square is 9 and x should be an even integer. So it is not possible. We will not get any such integer, okay, which will be even and square will be 9. So this is an empty set. Next is singleton set. Here singleton set means a set containing exactly one element is called a singleton set. So in a set, if you have got only one element, then we would call that set a singleton set. Like here, this is a singleton set. This contains only one element, that is 0. Here we can see there is one set contains elements x such that x is a member of integer and x plus 4 is equal to 0. Okay, so here we can see that if in place of x, if I put minus 4, then only I'll get 0. Okay, so there is only one integer which will satisfy this condition. Okay, so this set contains only minus 4. So this set has only one element, minus 4. So it is a singleton set. Okay, same way, there is a set containing elements x such that x is a natural number and x square minus 9 equal to 0. So we know that minus 3 square is 9, but minus 3 is not a natural number. Okay, 3 square is 9 and 3 is natural number. So this set will contain only 3. So it is a singleton set. Okay, in this same set, this one, okay, in place of n natural number, if you would have taken z, okay, then this set would have contained minus 3 and 3. So in that case, now this is not a singleton set because it containing more than one element. Next is finite sets. An empty set or a non-empty set in which the process of counting of elements surely come to an end is called a finite set. Okay, the number of distinct elements contained in a finite set A is denoted by n, and in bracket you write A. That means if it's written like this, that means this is giving you the number of elements in set A. Okay, and it is said to be cardinality. Okay, cardinality of the set. Examples of finite sets like set A 2, 4, 6, 8, 12, 10, 12. So here if you start counting the elements, so 1, 2, 3, 4, 5, 6. Okay, so here your counting process is coming to an end. Yes, so this is a finite set. And how many elements are there? 6 elements. So we will write like this, n, and in bracket A equal to 6. Okay, let B equal to set of all letters in the English alphabet. So there are 26 alphabets. So this set of letters in English alphabet is also a finite set, and number of elements is equal to 26. Okay, next, the set of all persons on earth is a finite set. Okay, it is possible for us to count, okay, persons on earth. Set of all animals on earth is a finite set. Okay, next, a set which is not finite is called an infinite set. For example, examples of infinite sets are here. The set of all points on the arc of a circle is an infinite set. The set of all points on a line segment is an infinite set. The set of all straight lines parallel to the x-axis is an infinite set. The set of all positive integral multiples of 5 is an infinite set. Okay, so your set of all positive integral multiples of 5 is an infinite set. Okay, so you can go on like this, 5 1 ja, 5 2 ja, 5 3 ja, so on with the positive integer, and same way you can go on 5 into minus 1, 5 into minus 2, and so on. So your counting will never end. Yes, so this is infinite set. Some more examples of infinite sets. So set of natural numbers is an infinite set. Set of all integers is an infinite set. Set of all positive integers is an infinite. Set of all rational numbers is an infinite. Set of positive rational numbers is an infinite. Set of all real numbers is an infinite, and set of all positive real numbers is an infinite. So this is all for today's lecture. Okay.